So a physical change alters only the state or appearance, but not the composition. And what I mean by the composition is that the actual atoms and molecules that make up that substance have not changed fundamentally. They're still the same atoms, they're still the same molecules. Their appearance may change, but fundamentally it's still the same compound. So they don't change their identity during a physical change. For example, boiling water. It's water in the pot, it's even water when it's steam, but both of those phases are still water molecules, and they're sort of shown here as space-filling sphere models. So the state changes, still made of water. Chemical changes, on the other hand, are where you do alter the composition of the matter. So kind of going back to John Dalton's quote, if everything is made of these atoms, and we know, going beyond what Dalton described, that things are also made of molecules, what you're changing is the actual configuration of those atoms or molecules that make up that substance. So at that level, the things are changing. Like one that we've probably all seen, I'd be surprised if you had never seen rust before, but rust is a chemical change. And there are a lot of distinct changes when something rusts. It becomes weaker, the color of the material changes, and turns into an orange flaky powder. So that's a rearranging or transforming of the original substance into different substances. So you're going from these iron atoms, and even in this sort of diagram here, right? These are all nicely ordered. In the iron oxide, there's less order to the molecules, and you've got now these red oxygen atoms that have inserted themselves between the yellow iron atoms. So rusting of iron is a chemical change. So usually physical changes are going to be involving state changes, are really the most common ones. So dry ice is one that you might not think about very much, but dry ice is solid carbon dioxide. And dry ice has the special property that at room temperature and room pressure, it goes straight from solid to a gas. So that's called sublimation, and that's a physical change, because these are carbon dioxide molecules, and the gaseous carbon dioxide is still carbon dioxide molecules. I will warn you, if you go to buy it, they will sell you a bag. There are some places where the distinction between physical and chemical changes breaks down a little bit. This one's fine. Sugar dissolving into water. You're taking crystal sugar, in this example on the left. That's solid sugar. And when you add it to water, the water molecules are taking the individual sugar molecules and separating them. And the water molecules surround them so that the sugar molecules can't stick to each other. The boundary is a little less clear for other substances dissolving. Another sort of physical versus chemical change, this is sort of a combination of things. So in this propane tank, you have liquid propane, and as that propane is released, it will go from a liquid to a gas, which is a physical change. But then if you burn that propane, then you're taking the propane molecules and you're breaking them apart into carbon dioxide and water, and it also releases a lot of heat. So if you're changing the composition of something, that's a chemical change. If you're just changing the really physical state of something, then it's a physical change. And those chemical and physical changes can be defined by something's chemical or physical properties. So a physical property, by sort of a simple definition, is a property that displays without changing its composition. For example, the smell of gasoline. You don't need to change the gasoline into something else to smell it. That's your nose picking up those molecules and telling your brain that's gasoline. So things like odor, taste, color, appearance, melting point, boiling point, and density are all physical properties. But you don't need to change the substance into something else to exhibit those properties. Chemical properties are properties that a substance displays only by changing its composition via a chemical reaction. And really, by definition, a chemical property is how a substance reacts with other substances. So under what conditions will it change chemically? So these can only be displayed by changing its composition. So the flammability of gasoline. You can only show that gasoline is flammable by burning it. Corrosiveness, acidity, and toxicity are other ones. So corrosiveness is how readily it reacts with other substances to essentially destroy them. Acidity is the proton concentration, and toxicity being, well, how it reacts with a living thing. Okay, so this is the first Mentimeter quiz. So which one of these best represents vaporized water? One vote already for A. So the hydrogens, I guess I should explain this a little bit. The white ones are hydrogens, the red ones are oxygen. Five, so far unanimous. 10, nice. Yeah, so go ahead and keep voting if you want. But yeah, the first one, it's A, right? So vaporized water is still going to have one oxygen and two hydrogens. It's still going to have that same format. So it should have changed on your devices there. You don't have to re-log in or anything. But this was the question we were supposed to do first. So I made it on a scale of 0 or 1 to 5 or something. So you can kind of set how confident you are. So if you're 100% confident that it's chemical, give it a 5. If you're 100% confident that it's physical, give it a 1. So copper wire is hammered flat. Chemical or physical change? Cool, okay. So I think you can say, so for the first one, we had one person say it was chemical. Looks like everybody agrees that nickel dissolving in acid to form a blue-green solution. Mostly very confident that that's chemical. Dry ice subliming. Sort of a mixed bag on dry ice subliming. And then one for a match ignites when struck on flint. Most people, though, say that's chemical rather than physical. So copper wire being hammered flat. Why is that physical and not chemical? Still made of copper. Still made of copper, even though it's hammered flat. Whether it's flat or round or anything else doesn't really matter. Penny's made of copper, and so are many wires. Nickel dissolves in acid to form a blue-green solution. Yeah, something dissolving. Usually, dissolving is a weird thing. But a nickel dissolves in acid to form a blue-green solution. So you're taking the metal and it's changing from that solid metal, adding it to a solution, acid. It's definitely chemical. Dry ice subliming without melting, that's the one we looked at. So subliming meaning going directly from a solid to a gas. So it's carbon dioxide when it's solid, it's still carbon dioxide when it's a gas. So it's not changing its chemical composition. And then a match ignites when struck on flint. So burning is always chemical. There's no situation where burning is not chemical. All right? So igniting, meaning that it starts on fire, chemical. Nice. Cool. So we'll try and I'll try and include more of those. I like the idea of being able to let people answer questions unanimously, or not unanimously, anonymously. Yeah, better for engagement. I'll write these in here though for the slide. So physical, chemical, physical, and chemical. And then this is the other one that we already did. Started on the wrong slide, but yeah, so if you're taking water and you turn it into a vapor, then it's still going to be made of water molecules. They're just going to be more spread out. All right, so that's all we're doing for chemical and physical changes. And now we're going to touch on energy, because energy really explains why everything happens. So if you go on to take Chem 2 especially, when you get to thermodynamics, thermodynamics really answers the question of why do chemical reactions happen spontaneously, and it all has to do with the energy. But we're not going to get so deep into that. Energy, simply put, is the capacity to do work. So work is defined as the action of a force through a distance, so really mechanical energy or mechanical work. If you push a box, if you move a thing, you're applying a force over a distance. Lots of examples of that. There are different kinds of energy. So kinetic energy is the energy associated with the motion of an object. So if you throw something or if you drop something. Potential energy is the energy associated with the position or composition of an object. So in this almost Looney Tunes-esque picture, we've got a giant, not anvil, but giant 10-kilogram weight being dropped off of a building.
That's so realistic.
So, I mean, this happens all the time.
I know.
So you got this 10-kilogram weight on top of the building. That's got a lot of potential energy. And then when it falls off the building, now it's got a combination of potential and kinetic energy. But as it falls, more and more of its potential energy is being converted into kinetic energy. And it's accelerating at, was it 9.8 meters per second squared towards the Earth. And then as soon as the weight hits the ground, now it's converting that kinetic energy into thermal energy. So even when you drop something and it hits the ground and it stops moving, that energy didn't just disappear. It just got converted into thermal energy. And I don't have the link on this slide, but in Chem 20 I have it. Somebody did all the math, right? So okay, if you have kinetic energy and you hit something and it stops, it gets converted into thermal energy. So it'll heat things up. So hypothetically, how many times would you have to slap a chicken in order to cook it? And somebody did the math, and it's an insane number of slaps. And then they also calculated how fast you would have to slap it once to cook the chicken. And it was, I don't know, it was something like over 3,000 meters per second. It was like multiple times, it was like 2 or 3 times faster than the fastest fighter jet is how fast you'd have to slap it. So, that is another example of when unit conversions are fun, because you could do insane things like calculate that. Okay, so energy, there's always a total amount of energy, kinetic or potential, and eventually I think we'll talk about chemical potential energy. But that energy is never created or destroyed, it's just converted from one form to another. And this is the law of conservation of energy. Energy is neither created nor destroyed. So it's always changing from one form to another. It can flow from one object to another. If you have a space heater, it's transmitting energy in the form of infrared light that your body is absorbing, and it makes you feel warm. The total quantity of energy, though, remains constant. This is why you can't have a perpetual motion machine. There's always energy lost to inefficiency. And by lost, I mean converted into heat. So objects with high potential energy tend to be unstable. Oh yeah, chemical potential energy is here. So chemical potential energy arises from electrostatic forces between charged particles that make up atoms and molecules. Most of the time we talk about that energy sort of being stored in bonds. So the forces that hold atoms and molecules together are, I guess in essence, made of energy. And sometimes breaking bonds releases energy, forming new bonds requires energy. And just like a physical system or this weight unstably balanced on top of a wall, if a molecule has a high amount of chemical potential energy, those are generally unstable. Classic example being TNT. Trinitrotoluene is a molecule that is highly unstable because it has a ton of chemical potential energy. So when you break those bonds and form new bonds, it releases all of that energy and forms lower energy bonds instead. So, summarize energy. Energy is always conserved in a physical or chemical change. It's neither created nor destroyed. Systems with high potential energy tend to change in a direction that lowers their potential energy. And it's the same for molecules as well. They're always trying to go to lower potential energies. All right, so that's all we're doing on energy. Told you we're going to go through these pretty fast. All right, so modern atomic theory. I've cut this down. I drew a little cartoon that we'll look at later to do like a brief history of the atom. So the atomic theory is the idea that all things are composed of atoms, right? All matter. Right? That was John Dalton in that quote that we had at the very beginning. And it grew out of observations and laws, and specifically these three laws: the law of conservation of mass, and so matter is neither created nor destroyed, the law of definite proportions, and the law of multiple proportions, which we'll go over. So law of conservation of mass: in a chemical reaction, matter is neither created nor destroyed. We looked at Lavoisier a little bit. He did those initial experiments with stuff burning things in sealed glass containers. So when a reaction occurs, the total mass of the substances involved in the reaction doesn't change. You're really just rearranging those atoms and molecules. And this law is consistent with the atomic theory. So the particles rearrange during a chemical reaction, but the amount of matter is conserved because the particles themselves are indestructible. Actually, the word atom comes from atomos, which was like a Greek idea. I cannot remember which Greek philosopher it was. It's in the book, I'm pretty sure. But meaning some smallest indivisible particle. Because some dude was sitting there and he said, what if I cut this in half? And then what if I cut it in half again? And what if I cut it in half again? And then in his mind he said, that cannot go on forever, so there has to be something that can no longer be cut in half. Now originally we thought that was the atom, and now we've got things like the Large Hadron Collider, which smash atoms. So there are smaller things. So if you were to take something like sodium, so sodium metal, let me zoom on this. Sodium metal, add chlorine to it. No, don't drop it in water. Add chlorine to it, then you'll get sodium chloride, which is table salt. And the masses of the sodium and the chlorine, as long as they're reacting completely, will be equal to the mass of the sodium chloride created. And sodium and chlorine are always pointed out because they're interesting, because we eat sodium chloride all the time. But sodium by itself is a highly reactive metal. If you drop it in water, it explodes. Chlorine is a highly toxic gas. If you breathe a little bit of it, you're going to have a bad time. But put them together and you get this very inert, really necessary molecule that is delicious. So if a log completely burns in a campfire, the mass of the ash is much less than the mass of the log. So what happens to the matter that composed the log? So was the matter that composed the log converted into energy? Was it composed present in the ashes but has a lower mass? Or formed gases that are released into the air? A. Yeah, so you're forming gases, and burning anything made of carbon is going to give you gaseous CO2 and gaseous water. Ash is always other stuff that's left over, and smoke is incomplete combustion. So matter is always conserved. The law of definite proportions is that all samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. So this is formulated by, in 1797 by Joseph Proust, who's a French chemist. I think that got cut off here. It just says Joseph Proust, a French. So for example, the decomposition of 18 grams of water. So if you take water and you break it apart into its constituent elements, you'll get 16 grams of oxygen, 2 grams of hydrogen, and an oxygen to hydrogen ratio of 8 or 8 to 1. And that is consistent. It doesn't matter if you get water here, if you get water from somewhere else on Earth, or even out in the deepest reaches of space, it'll have the same composition. And that's because the substance we know as water is made of 1 oxygen and 2 hydrogens. Okay, I believe this is the first one that's on that sheet. So the mass ratio of nitrogen to hydrogen in ammonia is 4.7 to 1. If a sample of ammonia contains 10 grams of hydrogen, how many grams of nitrogen does it contain? So it's 4.7 nitrogen, 1 hydrogen. This is a ratio. Ratios can be weird sometimes. Actually, this one's not too bad. Yeah. All right, so is it 4.7? 9.4, 14, or 47? 47. The way that you would do this is essentially what this is saying is this ratio of 4.7, I should say grams here, grams of nitrogen for every 1 gram of hydrogen. So you'd say if you have 1 gram of hydrogen, then you're going to have 4.7 grams of nitrogen. If I have 10 grams of hydrogen, then I'll have 10 times as much nitrogen as well, so it would be 47 grams. It's kind of a weirdish problem. It's just to illustrate this fact, and that you could say it scales. So let's say you have 2 samples of carbon monoxide are decomposed into their constituent elements. One sample produces 17.2 grams of oxygen and 12.9 grams of carbon. The other sample produces 10.5 grams of oxygen and 7.88 grams of carbon. So show that these results are consistent with the law of definite proportions. So essentially use these numbers, prove the law of definite proportions. Okay, so how might we go about proving that this follows the law of definite proportions? What is the law? Yeah, so the ratio of elements for carbon monoxide from one place should be the same as the ratio of the elements of carbon monoxide from somewhere else. So there's kind of 2 ways that you can do it, and 2 ways that are kind of the same way. So our one sample comes from one place that's 17.2 grams of oxygen and 12.9 grams of carbon. And then the other sample is 10.5 grams of oxygen and 7.88 grams of carbon. If we just divide those, you could divide them either way. It could be oxygen over carbon or carbon over oxygen. In general, it's a little bit nicer to try and get whole numbers. So you put the larger number on top. So what was that for the first one? Whoops. Say 1.3. Oh, I missed a decimal. 1.33. And then for the other one, did this follow the law of definite proportions?
It's not repeating though, but
yeah.
it's still.
Yeah, so here, even though that this one is 3, 3 repeating, and this one does like 3, 3. I'll rewrite these. 1 repeating. This one's 1.33248. Right, goes on. To our level of precision here, 3 sig figs, they're the same. Cool. All right, so the next law, at first might seem like it contradicts the law of definite proportions, because now we have the law of multiple proportions. But the law of multiple proportions kind of takes definite proportions and expands a little bit on it. So for the law of multiple proportions, when 2 elements, let's call them A and B, form 2 different compounds, the masses of the element B that combine with 1 gram of the mass of the element A can be expressed in a ratio of small whole numbers. So one of the key things about this is we can have, or I guess, molecules that are made up of the same 2 things. And carbon monoxide is actually a good one, because we can have carbon monoxide, which is just CO, or we have carbon dioxide, CO2, or you could have carbonate. All right, so there's all these different compounds that are combinations of carbon and oxygen. But we can describe the ratios between the carbon and the oxygen in each of these cases as a whole number. So for the first one, carbon and oxygen, there's, well, 1 atom of carbon for 1 atom of oxygen. Second one, 1 to 2, and then 1 to 3. And the 2 minus there being the charge. Now, of course, that's an example on the next slide. So carbon monoxide and carbon dioxide are both compounds composed of the same 2 elements, carbon and oxygen. And their mass ratios are going to be different from each other, but consistent for all carbon dioxide, consistent for all carbon monoxide. So the law of definite proportions is talking about everything of a single compound, and the law of multiple proportions is for all of the compounds that are possible, really. All right, so if we have hydrogen and oxygen, they both form water, and they can also form hydrogen peroxide. The decomposition of a sample of water forms 1.25 grams of hydrogen for every 1 gram of oxygen. The decomposition of a sample of hydrogen peroxide forms 0.0625 grams of hydrogen for every 1 gram of oxygen. Show that these results are consistent with the law of multiple proportions. Sorry, I kind of glossed over this. So it's the ratios also that, so it's the oxygen to carbon for carbon dioxide divided by the ratio of the mass of oxygen to carbon and carbon monoxide. Dividing those 2 will give you a whole number. So there's twice as many oxygens, twice as much mass of oxygen in carbon dioxide than there's in carbon monoxide. So for this, it's a similar thing, and very conveniently given 1 gram of oxygen for each, so that makes the ratio easy. So 0.125 grams of hydrogen per every 1 gram of oxygen. Divided by the 0.0625 grams of hydrogen for every 1 gram of oxygen. So essentially we've got 0.125 divided by 0.0625, and that equals 2. So it is consistent. Okay, now for my little cartoon. Brief history of the atom. So first, John Dalton had the theory of the atom, and he was the one who was like, oh, everything is made up of small, indivisible particles. And that's consistent across everything. And that was in 1808. And it wasn't until like almost 90 years later, J.J. Thomson didn't really get proof of the atom yet, but he used the cathode ray tube to prove that atoms have electrons. A cathode ray tube is also the same thing that's in a CRT TV. How many of you guys know what a CRT TV is? But that same technology is what J.J. Thomson was using way, way back in the day to create or to prove that there were electrons. Then later, almost 10 years, just over 10 years later, 12 years later, Robert Millikan did the oil drop experiment. And so he had this chamber where he diffused these really, really tiny oil particles. And then he would send them down, they would fall down into this chamber. And there's a negatively charged plate on the bottom. That's what this is. And by watching these, he could determine how long it took them to fall. And then he would use a cathode ray tube to shoot electrons through here and give these oil drops a charge. And based on that charge, if you had applied a negative charge to this plate and he had a negative charge on his oil drops, he could adjust the charge on this plate to suspend the oil drops in the air over the plate. And then through a series of math, calculate what the charge of an electron was. And then the other one that we're going to talk about here briefly is Rutherford's. Yeah, yeah, it's toilet paper. So this is from one of Rutherford's quotes about this. He did this gold foil experiment, though. He took a radiation source, and from that radiation source, he fired helium atoms, essentially, alpha particles, at a sheet of gold foil, very, very thin sheet of gold foil. And he expected, based on the theories at the time, which is the plum pudding model, that the atoms were just essentially this sphere of positive charge with little negative electrons inside. And then he expected these alpha particles to go straight through the foil. That's not what happened. They bounced back, or they bounced away, or they bounced in really, really crazy directions. And he said it's about the equivalent of if a tank fired a cannonball at toilet paper and it bounced off. Or came back and hit you, I think is what he said. So this is my tank firing at gold toilet paper. There's a lot more information about this if you want to know. It's in the book. You can go and look at that. I think it's pretty interesting. But unfortunately, no time for it. So Rutherford then proposed the nuclear theory of the atom with three basic parts. That one, most of the atom's mass and all of its positive charge are contained at the very center of the atom in a core called a nucleus. Two, that most of the volume of the atom is empty space, throughout which tiny negatively charged electrons are dispersed. And three, there are as many negatively charged electrons outside the nucleus as there are positively charged particles or protons inside the nucleus, so that an atom is electrically neutral. And everything wants to be charge balanced. So this all made a lot of sense. So although Rutherford's model was highly successful, some scientists realized that it was incomplete. So hydrogen contains 1 proton and helium contains 2 protons, but the mass of helium is 4 times that of hydrogen. So it was like, well, why is that? It was work by Rutherford again and one of his students, James Chadwick, who demonstrated that the previously unaccounted for mass was due to neutrons, or these neutral particles that also existed inside of the nucleus. So neutrons have no electrical charge, they are neutral. Neutron, neutral, right? They sound the same. Protons are positive, electrons are negative. The mass of a neutron is similar to that of a proton, slightly different. And a hydrogen atom contains only 1 proton and no neutrons. The helium atom is 4 times as massive because it has 2 protons and 2 neutrons. So the nucleus is extremely dense, contains over 99.9% of the mass of the atom, but occupies very little space. So as an analogy, you can think of the electrons like a cloud around the nucleus. They have negligible mass, but are dispersed in a large volume. And then, so just like clouds, atoms are mostly empty space. Except in the case of atoms, the electrons will push against the electrons of other atoms, and so they don't essentially cross boundaries. So when they bump into each other, they repel each other. And because of this, matter is way less uniform than it appears. So if the nucleus was the size of a period, the electrons would be 10 meters away. So it's like from here to maybe even beyond that wall is where the electrons would be if the nucleus was here and the size of a period. So it's very, very much all empty space. So a grain of sand composed of solid atomic nuclei would weigh 11 million pounds. And actually, neutron stars, if you're into space stuff at all, neutron stars are that. They're a star where the core is composed entirely of neutrons all packed together because of the intense gravity. You can also think of it like this. So if you had scaffolding, right? So if there's ever construction on the outside of a tall building, they put up scaffolding so they can get up the sides. So if you think of scaffolding like that, and then the scaffolding was the size of a football field and 100 stories high, it's mostly empty space, but if you viewed it from an airplane, it would look kind of like a solid structure. The nucleus would be the size of a pea inside of that football field of scaffolding. And so this is why when you touch something or you're wearing something or you're holding anything, this is why things don't pass through each other, is because the electrons are repelling. But it is all just empty space. If that didn't exist, everything would just pass through everything without ever making contact. So I wanted to summarize so far the structure of the atom. I'm just going to do it in here. But so structure of the atom so far as we've got it, we have a nucleus, and that's made of protons, which have a positive charge, and neutrons, which are neutral. And then we have everything around the nucleus, which are going to be the electrons, which have a negative charge. If you remember nothing else, remember this. These are the fundamental pieces of an atom, and the interaction between those electrons and the protons is what causes all matter to do what it does. And those are subatomic particles actually also. So all atoms are composed of those subatomic particles. Protons and neutrons have nearly identical masses. The mass of an electron is a lot smaller. I mean, these are all small numbers, right? Proton and neutron are both 10 to the negative 27 kilograms, but an electron is 10 to the negative 31 kilograms. So if your proton had the mass of a baseball, an electron would have the mass of a grain of rice. So when we're talking about the mass of an atom, obviously these are not very convenient numbers to work with. So they devised a different unit for talking about the masses of atoms, and that's the atomic mass unit. And they defined the atomic mass unit as 1/12 the mass of a carbon atom containing 6 protons and 6 neutrons. Why carbon? Because it's so abundant. Carbon-12 is very, very, very abundant. So the mass of a proton or a neutron is approximately 1 atomic mass unit, because they make up half of the mass of that carbon atom. Or each one makes up half. So the charge of the proton and the electron are equal in magnitude, but opposite in sign. Right, so protons are positive, electrons are neutral, or negative, sorry. Electrons are negative, opposite signs. So equal strength, kind of like equal strength magnets, except one magnet's a rice grain and the other magnet is a baseball. Neutrons are charged neutral. And this is a really important point because matter is usually charged neutral because the protons and electrons are normally present in equal numbers for like everything. When this falls out of balance, the matter will sometimes violently try to correct it by exchanging electrons. So static electric shocks are one example, or lightning is another example. So there's a huge charge imbalance between the particles in clouds and the ground. That charge will be balanced by a lightning strike. And it's differences in charges that drive a lot of reactions too. All right. now we're getting into the periodic table. So the number of protons in the nucleus defines the element. So here we have most of the elements. There are a few in here, man-made elements that have been named now, but all the elements, they're defined by their number of protons. And that's called the atomic number, which is given the symbol Z, which is from the German word Zahl, meaning number. Very creative. So helium has 2 protons. Carbon has 6 protons. So you get different periodic tables. This one doesn't have the names on it, but it has your symbols, atomic symbols, and atomic number, as well as the weighted average mass of all the isotopes. So each element is identified by a unique atomic number with its own chemical symbol. It's important that you memorize these symbols. There's a list of symbols and names to memorize, and then there's a couple different quizzes for helping to memorize those in a sort of fun way. But you could also make flashcards. I always practiced memorizing elements by getting a blank periodic table, and then you could put it into like a clear plastic, like a 3-ring binder sleeve, and then use a dry erase marker. And then you could fill it in, or you could print out a bunch of blank periodic tables and just fill those in over and over and over again. It's kind of a rote memorization thing. So 1 or 2 letter abbreviations listed directly below its atomic number on the periodic table, and then the mass underneath. Most of them are based on English names, but some of them are not. I always mess this up, but well, copper is cupric. That's why it's Cu. Silver is argentum, I believe. Something similar to that in the Latin name, I believe. I can't remember gold right now, or mercury, but those are also Latin names. Along with tin. Tin is stannous. And I can't remember what antimony is. Right, so there are some on here that are really weird. A lot of them kind of make sense. Some of the ones that do end up being tricky are things like sulfur is S, sodium is natrium. So hypernatremia or hyponatremia would be low sodium, be a medical term. K is selenium, but like strontium, sodium, and sulfur often get mixed up because they all start with S. So just be aware of those when you're trying to memorize them. Cool. So chemical symbols, names. It's a shorthand. Do you want to point this out? When you're writing out the name of a chemical, they're not proper nouns. So technically they should be lowercase unless they're starting a sentence. All right, so carbon. Also, if we have an element quiz, please don't switch the B and the R on carbon. It's a very different word, if you know Spanish. The other thing is that for these chemical symbols, the first letter has to be capitalized, and the second letter has to be lowercase. They can't both be lowercase or both be capitalized. And that's to prevent trying to think of an example, but I'm not finding one. I was going to say situations where if you write 2 capital things, 2 capital letters next to each other. Oh, here's one. So if you write cobalt as capital C, capital O, it's going to look like carbon monoxide, capital C, capital O. So cobalt is lowercase o. Okay, so isotopes are, they have the same number of protons, but they have a different number of neutrons. So pretty much all atoms of a given element will have all the atoms of the same element will have the same number of protons. Most of them, for most elements, will have the same number of neutrons, but there are some that have multiple stable configurations, and some of them that exist in nature with 2 different numbers of neutrons in roughly equal quantities. One of those is chlorine, actually, which I believe is 35 and 36. So you can have chlorine 35 or chlorine 36, and they're almost equal, so you get this mass on the periodic table, 35.45. So for example, neon atoms all contain 10 protons, but they could have 10, 11, or 12 neutrons. And all three neon isotopes exist. Each has a slightly different mass, and each exists in different abundances. So the relative amount of each different isotope in a naturally occurring sample of a given element is roughly constant. So those are called the natural abundance of the isotopes. The way that we represent these different isotopes is with this isotope notation. So A is the number of protons, the mass number is A, which is the number of protons plus the number of neutrons. So that's the total mass of a single isotope. So isotopes are symbolized with the mass number to the top left, atomic number to the bottom left of the chemical symbol. So those three isotopes of neon would each have 10 in the bottom left, because that's the number of protons. That stays the same. But the mass number A is going to be 20, 21, or 22, depending only on the number of neutrons. So you can always find the number of neutrons by taking the mass number and subtracting the number of protons. Another common notation, because the number of protons is always going to be the same, is to just write the symbol with the mass number or the name with the mass number. So neon 20 is neon with a mass number of 20. Still has 10 protons. That doesn't change. And so for neon, 20 is the most abundant. So 90% of neon is going to be neon 20. 0.27% is neon 21, and about 10% is going to be neon 22. 10, 11, or 12 protons. So Dalton was not completely correct in stating that all atoms of a given element have the same mass. All right, we just talked about isotopes. But the important thing here is that when we calculate, these masses that are calculated on the periodic table are the average mass. And that's our atomic mass. So mass number and atomic mass. So that's what you find directly beneath all those symbols. And it's the average mass of the isotopes that compose that element. And it's a weighted average. So for example, for chlorine, oh good, yeah, see? Oh, it's 37. So naturally occurring chlorine consists 75% of chlorine 35 atoms and 25% of chlorine 37 atoms. And so we calculate its atomic mass based on its abundance and the masses of those isotopes. So these are exact masses. So chlorine 35, we would take the percent converted into a decimal. So the proportion of chlorine 35 multiplied by its exact atomic mass, and that would give us this number. And then we take chlorine 37, multiply its exact mass by its proportion abundance to get this number, and then adding those together gives us the weighted average. Must be bromine that's 50-50. We got a couple. No, we only got one example, huh? So the reason, before we work on that example, the reason that it's a weighted average is by multiplying by this proportion, we're sort of giving that more weight. We're giving that mass more importance. So because 75.77% of chlorine atoms is chlorine 35, we're saying when we calculate the mass of this, we want 0.75 of that ending mass to be the result of the 34.97. So it's making that mass more important than the other mass in the calculation. There's also why it's not calculated like a regular average. All right. So magnesium has 3 naturally occurring isotopes with these given masses and natural abundances, respectively. So respectively meaning that the first mass given goes with the first percent given. Second with second and third with third. Calculate the atomic mass of magnesium. the first key thing on these problems is always convert the percentage into a decimal. Not actually if there's any time where you use percentages as percents, except for when you're explaining something. All right, so I like to set these problems up this way, calculating it for, well, it depends on how you want to do it. Because you can type all this into your calculator in one shot, but I think it also helps to visualize it when you're learning it. This also illustrates the fact that, or it illustrates how the percentages are affecting how much each mass is contributing to the final average mass. So each of these is pretty close together, right? 23.99, 24.99, 25.98. But when you multiply them by the percentage, convert it into a proportion, so 78.99% becomes 0.7899, you see that the results of those numbers are very different, and that this 78 is contributing the most to what's going to be the final mass when we take these and we add them all together. So it'd be 24.309099. Also good practice for keeping track of sig figs. Final answer 24.31 AMU. And I know somebody asked me to go over one of the questions from the reading quiz, which I think was actually the reading quiz for today. But it was asking based on, it gave an isotope, like an element that had two isotopes, two different masses. One was like 60 or 70%, the other one was 40 or 30%, and said which one is going to, oh, it said where would the mass be, and it gave you some different ranges. I think this illustrates kind of why in this one it's going to be closer to 23.99 because most of the final mass is coming from that calculation because it's the highest proportion. It's kind of like if you took, I guess if you took M&Ms, if you took red M&Ms and you took green M&Ms, and 60% of the M&Ms in the bag were green, and 40% of the M&Ms were red, you would say that most of the M&Ms are green. And so when you pull out a handful of M&Ms from that bag, you're probably going to get more M&Ms that are green than red.